Hello. This video is going to be the first lesson in a multi-part series that I'm going to be making to attempt to teach AP Physics 1 Algebra Based. This material will be meant for students who, like me, are attempting to self-study the exam. I am making the lesson material as I learn the material myself. So, let's learn together. I am currently awaiting approval from my school to actually self-study the exam, but I'm learning now just in case they say yes, because they don't really have a reason not to. So this lesson today is meant to cover topics 1.1 and 1.2. Unit 1, the unit we're going to be working out of today, is titled Kinematics. Kinematics is kind of the study and representation of motion in environments that have a constant acceleration. So a really common example for this would be if I were to take this marker here, hold it out, and then just drop it. Now, I'm assuming you've taken a physics course before and you know that Earth's gravity is pulling us down at 9.8 meters per second squared. So if I drop this, its acceleration is constantly 9.8 meters per second squared. So that's what kinematics is, in case you forgot. So let's start with topic 1.1. Topic 1.1 asks you, the student, to understand the concepts of vectors, scalars, and the difference between them. So let's start with a scalar. So a scalar is a quantity with magnitude. Pretty simple. A lot of things fit into this category. Some examples would be speed. The standard unit for speed is meters per second. It's calculated with the distance you travel over a period of time. Another example would be mass. Its standard unit is the kilogram. Mass is a measure of how much matter you have in something. So I weigh about 125 pounds. That is my weight. The unit for that is pounds in the United States. My mass is approximately 55 to 56 kilograms, give or take a few. So that means I have approximately 55 to 56 kilograms of matter in my body. You can convert this to the initial unit for mass in the metric system, grams. We can convert it pretty easily. The root word here, kilo, means 1,000 grams, 1,000 grams, which is how many grams are in a kilogram. 1 kilogram has 1,000 grams of mass in it. So I have approximately 55 to 56,000 grams of mass in my body. My phone, it weighs, I don't know, maybe a pound or two. So it has less than a kilogram, I think. I believe a kilogram is 2.5 to 3.5 pounds, something along those lines. Another example of a scalar would be time. In AP Physics 1, the standard unit for time is seconds. Occasionally, it will... Forgive my handwriting. I can't see the edge of this when I'm writing. So occasionally, you will be asked to solve problems in different measures of time. You may be asked to calculate something's speed in miles per hour. In which case, you have to convert it, but it will almost always be seconds. Another example of a scalar is distance. The standard unit for distance is meters. Distance is used in the calculation of speed. Distance and time together are used to calculate speed. Distance, the meters aspect of this here, divided by the time, the seconds here. that is the concept of a scalar. Let's get into the concept of a vector now. So a vector, if you've ever seen Despicable Me, and you remember Vector's introduction, he very, very, very boisterously claims that he himself, his name is Vector because he has both direction and magnitude. That's what a vector is in physics. A vector is a quantity with both direction and magnitude. As Vector from Despicable Me 1 claims so very boisterously. We all love him for it. So a vector, it always has a direction. If you don't include your direction, you're given a scalar, and like, that's useless. And it's really bad form to answer your questions without including your direction. I would not be surprised if your grader on the AP exam would mark your answer wrong if you did not include a direction when you're talking about a scalar, because at that point you are straight up giving the wrong answer. You're giving a scalar quantity when you're being asked for a vector quantity. That's not good. Do not be that guy, please. So some examples would be velocity. Velocity, like speed, is measured in meters over seconds. Velocity is the rate of change for your displacement. Displacement is a different quantity, but it's very similar to distance. Let's give a quick little example. Let's start with the definition of displacement. So, displacement is measured in meters, like distance. Now, students often mix these two up, which, for good reason. They use the same unit and they're pretty similar concepts. And in a lot of scenarios, they will be the exact same value. You just need to understand conceptually the difference between them. So distance is how far something has gone in a scenario. And displacement is how far something has gone from its original position in a scenario. There's a very big difference. If I were to leave my house right now, which would be a very bad idea because it's almost 10 o'clock. If I were to leave my house right now and I were to walk 5 kilometers away, my distance would be 5 kilometers because I have walked 5 kilometers. My displacement would also be 5 kilometers because I am 5 kilometers away from my house where I started. If I were to then turn around and walk 2.5 kilometers back towards my house, my distance would be 7.5 kilometers because I walked 5 kilometers away, I turned around, and I walked 2.5 kilometers back. I walked 2.5 kilometers farther than I did before. My displacement would be 2.5 kilometers because I walked 5 kilometers away from my house and then came closer to my house. I decreased my displacement. I got closer to my origin point. I got closer to my house. Do not mix these two up. So you can calculate your velocity with these. I'm so sorry. I'm a bit of a stutterer. Your displacement is used in your velocity in calculation for velocity. Distance is used in calculation for speed. If you mix them up, you will be giving speed with a direction, which makes no sense. Because at that point, just give velocity. So let's say that I made that whole scenario. I walked 5 kilometers away and came 2.5, and then walked 2.5 kilometers back. Let's say that took me 100 seconds. Makes calculation easy. So my distance is 7,500 meters because a kilometer, like a kilogram, has the root word kilo, which means 1,000. Kilometer, 1,000 meters. So my speed, the symbol for speed is S, is equal to d over t, distance over time. 7,500 over 100 equals 75 meters per second. I am literally the fastest human on earth. Trust me. Look at me. I'm very obviously an athlete. So my velocity is equal to displacement over time. The formulas look the exact same. Don't worry about that. Worry about the word displacement, distance. Remember to use displacement here. So my displacement, I walked 5 kilometers away and came 2.5 kilometers closer to my origin. So my displacement is 2.5 kilometers. 2,500 over 100 equals 25 meters per second. There are different numbers here. You need to understand this concept. Try not to let this trip you up. It trips a lot of people up in the beginning. Practice, it will get really easy after a little bit if you forgot from your first physics class. Oh, that's really bad. Hold on. I'm going to move you back a little bit so that you can reach the charger. The device I'm recording this on is on 3%. I did not realize, and it gave me a warning, so I apologize for the interruption. Perfect. There we go. I think that's a better angle. You can see things better. So there's the difference between vectors, scalars, and your difference between speed and velocity. Those are very different things. So let's go back to examples of vectors, because there's a few more. There's just one more I want to give you, really. I'll give you two. Acceleration. Acceleration is measured in meters per second per second. I'm just going to write the shorthand version, meters per second squared. Acceleration is a measure of the rate at which your velocity is changing. So if we go back to earlier when I was very, very, very rudely dropping my marker, its acceleration is 9.8 meters per second squared. This means that its velocity is increasing by 9.8 meters per second in the direction of Earth every second. So if I drop it and it somehow falls for 1 second, it literally falls through the floor, its velocity will be 9.8 meters per second. If we let it fall for another second, 2 seconds will have passed and its velocity will be 19.6 meters per second. It's increased by another 9.8 meters per second. And one more that I want to give you is angle. Usually when you think of angles, you think of them in terms of degrees. That is that you can measure them in degrees. You can also measure them in something else. You can measure them in something called radians. So if you are a computer science student, you will likely have already, if you are a computer science student and you have done slightly complicated programs that involved angles, you will likely know what a radian is. For those people who don't know what a radian is, let's look at a circle. Pretend that this is a perfect sphere. I'm an exceptional artist, trust me. So, in one circle, there are 360 degrees. You can split this circle into 360 slices, and each slice is 1 degree. You can also split this circle into 2 pi slices. One of those slices is 1 radian, I believe. Yes. So, You can measure your angles in degrees or radians. If you look at your calculator on your phone, it will often be automatically set to radians. It could say rad. That's a common shorthand for it. If you've taken a geometry class before this, which I'm really hoping that you did, because you will need to understand geometrical concepts for even the next lesson, you will have likely had to switch your calculator from radian mode to degree mode whenever you learned cosine, tangent, and sine. So angles must be given a direction as well, because if I take this marker, let's say that its angle is 0 degrees, and I rotate it to 90 degrees, 90 degrees can mean a lot of things. If we're starting from here, 90 degrees could either be here, where it actually is, or here, another way. So we need to give a direction. So there are two directions that we have, clockwise and counterclockwise. Pretty intuitive. A lot of people use it in everyday life, relatively speaking, on a clock. So this way, 90 degrees. For me, this is a clockwise rotation. Yeah, it's a clockwise rotation from my perspective. From your perspective, it should be a counterclockwise rotation. If you forgot what clockwise rotation is, look at a clock. Here, I have a watch here. Look at this watch. The hands move from the 12 o'clock position this way. This is counterclockwise. I'm so sorry. The hands move from the 12 o'clock position this way. This way. This is clockwise. Going the opposite direction is counterclockwise. Pretty intuitive. Pretty easy. So those are vectors and scalars. So College Board let's see. So a very common question for very beginner physics is asking you for the average velocity in a situation. So let's plot out a position time graph real quick. The y-axis is our position, the x-axis is time. And let's say that, let's write out an actual equation for this. This will be helpful later. P of t, position in relation to time. Let's call it 5t squared plus 3t plus 7. So that would give us something like that. So our average velocity is the average velocity throughout an entire situation. So let's say our situation is from t equals 0 to t equals 5. Our average velocity will be calculated using the change in time, 5 seconds, and your average displacement. So if we want to calculate that, we can take 5 and plug it into our function here, p of t. So p of 5 is equal to 5 times 5 squared plus 3 times 5 plus 7, or 25 times 5, which is 125 plus 15 plus 7, 15 being 3 times 5. 125 plus 15 is 140, plus 7 is 147. So in that time, in 5 seconds, they have moved 147 meters. This is our displacement. So our average velocity would be 147 over 5. That would be close to 30 meters per second. Let's just be easy and write roughly 30 meters per second. Of course, I know that's not the actual metric, but it's close enough. Now, let's say we want something else. We want something called instantaneous velocity at exactly 5 seconds. Instantaneous velocity is your exact velocity at any one point in time. So you could count. So If you remember from geometry, tangent lines. Tangent lines are lines that intersect a function at exactly one point. They don't exist for constant slope functions, but they do exist for quadratic functions like this. So our instantaneous velocity would be equal to the slope of that tangent line. But how do we get that? I mean, there's no obvious way to do it. This is where a very special formula comes in. I'll explain. So here's the formula. Let's say, so look at every single term in our original function. So first, we filter out all the terms that don't have variables. So 5t squared has a variable, so we can include it. 3t has a variable, so we can include it. 7, it has no variable. It's a failure, so we do not include it. So here is the formula. N times x to the power of n minus 1. N here being the exponent of the variable. So let's look at our first term, 5t squared. Our exponent for the variable t is 2, meaning n here is 2. So if we take 2 times the current leading coefficient, 5, we get 10. So we get 10 times t to the power of 2 minus 1, or just 1, so 10t. Let's look at our second one, 3t. Now, if you remember, every single variable or every single number that doesn't have a visibly written exponent will always have an exponent of 1. So we can plug 1 in for n for our equation here. So 3 times 1 is 3, and times t to the power of 1 minus 1, or 0, which, if you remember, anything to the power of 0 is equal to 1. So 3 times 1 is 3. So we can take these two terms and write a brand new function. Let's call it v of t is equal to, and then let's put in our terms here, 10t and 3. This is a brand new function that will give us the velocity of the tangent line at any specific point. Or even, it will give you the velocity, or I'm so sorry, it will give you the slope of at any one specific point, which may be a pretty foreign concept for people who haven't taken calculus yet, because if you remember from Algebra 1, the formula for slope requires 2 points, x1 and x2, y2 and y2, or y1 and y2. But if we only have 1 point, how do we get that? We use something called a derivative, which is what we just did. The formula I gave you, n times x to the power of n minus 1, this is called the power rule of derivatives in calculus. A derivative is the slope of a point at the slope of a line at any one point. So here, this is the derivative function for this function. So let's get the instantaneous velocity from t equals 5, like we wanted to. From the start, v of 5 is equal to 10 times 5 plus 3 is equal to 53. So our object here, non-specified object, is going 53 meters per second at t equals 5. That's pretty darn quick, if you ask me. So yeah, this, what was I saying? Right, this is instantaneous velocity here. That should finish the, is there anything else I'm forgetting? Let me check. I have my lesson notes on my phone. I did forget something. I'm very, very glad I checked. What are, you may be asking yourself, or you may have been asking yourself earlier in this lesson when I was re-explaining the concept of acceleration, how can you identify when acceleration is occurring? There are 3 conditions. There are 3 scenarios. Change in velocity. Change in velocity is a very clear-cut sign of acceleration. I drop this. I know, I'm so mean. After 1 second, its velocity has gone from 0 meters per second to 9.8 meters per second. That is a sign of acceleration. Another one is change in direction. If I take this here and it's already falling, and then I just push it, that is a sign of acceleration on acceleration. It's falling, or let's say it's falling at a constant rate, and then I push it to the side. That is a sign of acceleration. I accelerated it towards this light here, the sun. And then the last condition is both. Both of these. If I drop this and then it's under the acceleration of gravity. It's increasing its velocity. It's changing its velocity. If I then push it, that is a change in direction, which is another acceleration, which switches it to both. This is how you can. That's how you can identify acceleration in problems. But I remember when I was taking Physics 1, before I actually thought it out, I was asking myself why I kept forgetting that change in direction is a sign of acceleration, because I never really thought it out. I never tried to explain it. So I kept forgetting because it wasn't that intuitive. Acceleration, change in velocity. Change in velocity is pretty easy. Change in direction, how does that relate to velocity? This gets into two-dimensional vectors. Vectors that move in the x direction, or that can move in the x direction and the y direction. So let's plot out. So let's say that you run 5 meters in the positive y direction at a constant rate. Let's say that it takes you 1 second to get there. So it takes you going at 5 meters per second. Or no, let's make it easier. Let's say that it takes you 5 seconds to run 5 meters in the positive y direction. So you're moving at 1 meter per second. But then suddenly you turn right. You go 1 meter in the positive x direction. And let's say it takes you 1 second. This looks pretty similar to something, actually. If you connect the vectors, it's a right triangle. Think back to before you made the turn. All of your change in distance was in the positive y direction. But now that you've made the turn, 5 meters is just a leg of a right triangle here. They coincide perpendicularly. So once you've made that turn, 5 meters is now a leg of a right triangle, which means that your the greatest displacement, the greatest distance is in this side here, C. And if you take that, if you remember Pythagorean theorem, we can use that here because the two vectors, when you combine them, they combine perpendicularly because they're going in perpendicular directions, like the x and y axes, because they're going purely x and purely y. So if you remember our formula, our Pythagorean theorem, a squared plus b squared equals c squared. 5 and 1 are a and b here, so 25, 5 squared, plus 1, 1 squared, is equal to c squared. If we square root that, we get the square root of 26 is equal to c. So the square root of 26 is equal to our displacement here. That took us 6 seconds. So I'm going to pull up Desmos on my phone here. So the square root of 26 is equal to roughly 5.099. And then if we divide that by the total time, we get, here I need to do radical 26 over 6. So before we make the turn, our change in our velocity is 1 meter per second. It took us 5 seconds to travel 5 meters. And then we take another second to travel to the right, 1 meter. So our total time elapsed is 6 seconds. And if we divide this number by 6, we get roughly roughly 0.85 meters per second. This is a change in velocity. It's not as clear cut. You have to do some calculation to actually see it, but this kind of proves that a change in direction is a change in velocity, which makes it acceleration. See if there's anything I forgot. I don't believe there is. That concludes the first lesson in this course. Have a good day.